In this video, we're going to look at the speed of a wave on a string and also the mathematical representation of a wave. So first, the speed at which the wave moves to the right in this picture depends on how quickly one particle of the string is accelerated upward in response to the net pulling force. And so we can find the velocity of any wave traveling on a string by the square root of the ratio of the force applied on the string, or the tension, divided by the linear density. Now, the linear density is the mass per unit length. So just looking at this formula, we can see a few relationships. Increasing the tension increases the speed at which a wave can move in a string. Increasing the linear density would decrease the speed at which a wave can move along the string. So let's take an example here and use this formula. And so we have transverse waves that travel on each string of an electric guitar after the string is plucked. And the length of each string between two fixed ends is 62.8 centimeters. And the mass is 0.21 approximately grams for the highest pitch E, and it's about 3.32 grams for the lowest pitch E. So if each string is under a tension of 226 newtons, we want to find the speed of the waves of the two strings. So everything's the same in these two except for the mass. The length is the same, the tension is the same, the mass is different. So that means we have a different linear density for these two strings. So if we want to find the velocity for the high E, we put in the mass for the high E, and that gives us 826 meters per second, the speed at which the wave travels along the high E string. And putting in the greater mass here for the low E, we find that it travels at 207 meters per second. That is a big difference here. Big difference between the high E and low E. So sound can travel, and the wave that's traveling through here, this transverse wave of plucking the string, is traveling much more quickly in the high E than it is in the low E. Let's look at this conceptual example here, in that if we have a wave that is moving to the right as pictured here, and we consider just one particle that is moving up and down, and the question is the speed of the transverse wave, so the rate at which the wave moves to the right, is that the same as the speed at which the particle, this particle right here, moves up and down? And a lot of times we might think that, oh, the speed of the wave is the speed of the particle as well, which that's not actually the case, because this speed of the wave here is going to be constant unless there's some damping that's involved, and that might slow it down slightly. But that speed to the right is going to be a constant speed, whereas the speed of the particle is actually going to abide by simple harmonic motion. So this is going to be a wave function. Think back to those wave functions that we had in the last unit of the v equal to the negative a omega sine omega t. That's what the velocity of this particle is going to be. It's going to have that waveform and that wave function. So that brings us into the mathematical representation of these waves. And we had a mathematical representation before, but remember, that was a little different. That was the representation of simple harmonic motion and the wave function of simple harmonic motion. Now in this unit, we're going to look at wave functions as the wave themselves, the waves that are moving through some media. So it's the motion of the wave particle. And these functions aren't going to be displacement versus time, velocity versus time, and acceleration versus time, but a y versus x. And so this is our typical Cartesian coordinate system. And this actually traces out the wave itself. And so in a wave that is moving toward the positive x, or moving to the right, we have the wave function of y equals a sine of the quantity 2 pi ft minus 2 pi x over lambda. Now, what are these symbols here? Well, t is our time that we're talking about, so we are time dependent, and f is our frequency, lambda is our wavelength. But notice this y is a function of both time and a function of the position here. So it's a little more complicated in the wave function than what we had last unit, because it's telling a little more of the story. Now, the only difference we would have is if we're moving toward the negative x or moving to the left, our wave function becomes y equals a sine of the quantity 2 pi ft plus 2 pi x over lambda. We won't necessarily do a ton of math dealing with these functions. However, we do need to be able to recognize, given a function, can we pull out our frequency, can we pull out our wavelength, or vice versa. If given a frequency and wavelength of a wave, can we write this function?